A question about a molecule that has one carbon, four hydrogens, and oxygen. There's three possible ways. Here's three ways that you can draw uh, the structure. Okay, so you'll notice these are three possible isomeric structures because the way the atoms are connected are different. Note that this carbon has two hydrogens and this oxygen has two hydrogens attached to it. Whereas over here, the carbon has three hydrogens and the oxygen has one. Whereas here, your oxygen has the three hydrogens and the carbon has one. So these would, if all of these existed, they would all be isomeric structures. Okay? But in fact, only one of these three structures exists in nature. The way four hydrogens, a carbon, and an oxygen, if you find them in a molecule, there's only one way you'll find it in nature. Only one of these structures is consistent with reality. Okay, so if they all existed, they would be called isomers, but only one of these happens to be uh, consistent with reality. So let's try to figure out which one by doing formal charges. We don't have to worry about the hydrogens. All of the hydrogens follow the duet rule, so we're okay with those. Okay. And if you look at the carbons, okay, this one has octet. The oxygen follows an octet here. This carbon follows an octet here. Octet rule. Four pairs around it. This oxygen has an octet around it. This carbon has an octet around it, and this oxygen has an octet around it. Okay, so you can't use the octet rule as a way of determining which is better. So what we need to do is look at formal charges. So like I said, all of the hydrogens here have single bonds. So let's just look at the formal charges of the carbon and the oxygen. So carbon by itself, remember, by itself, carbon should have 4. Okay. It appears to own in this structure 2 in the lone pairs plus 1, 2, 3, 3 singles. Okay, so it's involved in 3 bonding pairs. So half of three pairs would be 3 singles. So 5, 4 minus 5. The formal charge of carbon here is 4 minus 5, which is going to be -1. Okay, this oxygen over here, formal charge is 4. It appears to own how much? Again, a lone pair, so that's 2, plus 1, 2, 3 pairs. Half of 3 pairs is 3 singles. It appears to own 5. So formal charge of the oxygen here is, a free oxygen atom. Sorry, group 6A. So free oxygen atom will have 6 valence electrons. So 6 minus 5 is +1. So the formal charges here would be -1 and +1. Okay. Now let's take a look at the other ones here. Carbon, okay, here would have 0. So by itself, carbon would have 4. It appears to own 4. Why? Because you have 1, 2, 3, 4 pairs around it. No lone pair, so 4 minus 4 is 0. The oxygen over here, a free oxygen atom would have 6. Okay, and it has 2, 4. Okay, free oxygen atom has 6. And it appears to own 2, 4 from the lone pairs. And then half of these 2 bonds, so +2 would be 6. So a formal charge of oxygen is also 0. So here's a situation where all your formal charges are 0. Okay. And finally, the last one over here, carbon by itself would be 4. It appears to own 4 from the lone pairs, plus 2, half of the 2 pairs, that would be 2 singles, that would be 6. 4 minus 6, your formal charge on the carbon is -2. Okay, so this is -2. And your oxygen over here by itself should have 6. it appears to own 1, 2, 3, 4. Half of the 4 pairs will be 4 singles. It has no lone pair. 6 minus 4 is plus 2. So the oxygen here has a plus 2. Okay? So obviously, this is really bad. Okay, you have minus 2 and plus 2. And what's even worse here, you have a negative on the carbon and a positive on the oxygen. If you recall, oxygen is more electronegative, so that's even worse. Here, you have, it's not quite as bad, it's just plus 1 and minus 1, but look, your oxygen has the positive formal charge and your carbon is a negative one. It's preferable for the oxygen to have a negative formal charge. Okay, so the most likely structure is this one. In fact, this particular molecule is called methanol. Okay?